Assalamualaikum warahmatullahi wabarakatuh. Greetings everyone. Today I would like to conduct a presentation about final project of numerical method report with the topic of CFD based optimization of the wave making characteristics of ship hulls. So before I begin, let me introduce myself. So my name is Addino Dimas. I'm from Naval Architecture and Marine Engineering batch 2019 with the NPM of 1906356916. So these are the table of contents of my final project. Consists of introduction and then objective, initial thinking of problem, assumption, process flow, mathematical model, result, conclusion, and last but not least, references. So let's begin with introduction. In recent times, ship optimization based on computer simulation has become a decisive factor in the development of new and economically efficient and environmentally friendly ship hull forms. An important task at an early design stage is the optimization of the hydrodynamic properties of the ship hull. In order to do so, early in the design process, a novel hull from optimization approach has been developed and implemented. The optimization process is fully automated, requiring no user interaction, however, permitting it. The steady wave system of a ship moving through otherwise calm water is approximated by means of CFD or computational fluid dynamics simulation applying the state-of-the-art nonlinear free surface Rankine panel module of the ship flow system. The proposed optimization method aims at an improvement of the wave-making characteristics, like the minimization of the energy losses associated with the wave formation along the hull. Let's move on to the objective. The objective of this project is to control the optimization process flow and improve the system indication by tracing identification by tracing hull variations up to their respective fingerprints in the spectral distribution and in the wave pattern resistance. So what is the initial thinking of problem? For this project, we begin with application of comparing different hull shapes of variant in terms of their hydrodynamic performance. And then we get to have the valuable for CFD-based hull optimization. The last one, we finally get the nonlinear free surface Rankine panel solvers that are frequently used by ship model basins, shipyards, and consultants for fully automated hull shape improvement. We continue with the assumptions. So we have the length, the breadth, and the draft that are the vessel length, width, and the draft respectively, or L, B, and T. A pentamaran is composed of the central main hull being 2 times longer than the outriggers. They all have the dimensions of L per B equals to 10 and B per T sama dengan or equals 1.6. The stagger Lx is defined as the longitudinal distance between midsection of the central main hull and the outriggers, positive for outriggers towards the stern. The spacing Ly is defined as the lateral distance between the center plane of the main hull and that of the outriggers. So this is the table that we gain. These two parameters are symmetrically varied, which is defined in the table below. So we have the main hull outrigger 1 until 4 with 5 cases, and each case have 2 coordinates of L. There is Lx and there is Ly with various numbers as well. And then the panel region of the free surface is extends about 1.5 of the ship length upstream, 3.0 of the ship length downstream from the body, and 1.8 of the ship length sideward of the ship. Due to the symmetry, only a half of the ship and free surface is taken into account in the computation scheme. The effect of the remaining half of the computational domain is incorporated while calculating the influence coefficient by the reflection of the discretized elements. The hull is discretized by 450, 305, plus 415.5 panels, and the free surface by 1050 panels. The wake surface behind the hulls is discretized by 0.515 panels. All right, so let's start with the process flow. So what we do first is we do the initial quality assessment. First, we have the parent or interim hull form, and then we get to determine the flow simulation by using CFD. So we have the performance assessments afterwards using WCA. Yeah, the parent or interim hull form itself can be used to have the detailed shape evaluation. So after that, we get to perform initialization, where we reinitialization of the optimization task like variables, constraints, or bounds. So after that, we have the systematic full perturbation analysis and systematic variation of design variables like flow quantity related. So yeah, in other place, we also gain transfer matrices. After initialization, we perform sensitivity analysis, where we will evaluate the gradients like MOM, constraints, or bounds itself again. And then after that, we gain the gradient matrices. The next one is the whole improvement, where we minimize the objective function, implying constraints like iterative scheme, and then after that, we generate the improved full form and predict the gains or changes. So yeah, after that, we get to perform the hydrodynamics optimization approach. What is it? It is actually the present of optimization approach that aims at an improvement of the wave making characteristics like the minimization of the energy losses associated with the wave formation along the hull, which can be measured in terms of the free wave spectrum and the wave pattern resistance. So in hydrodynamic analysis, the flow analysis comprises the evaluation of the nonlinear free surface wave flow by a CFD simulation and the analysis of the energy components contained within the wave pattern. In this CFD simulation, the boundary value problem of potential theory is solved numerically. In order to gain the numerical solution, first we compute the base solution like adopting a Newman or a double body condition 9 at the undisturbed free surface. Then we use the velocities from the previous step to compute the free surface elevation. And then we move the free surface panels to the new free surface computed at the previous step. The last one, we move the latest known flow solution to the adjusted free surface panelization. Right. Oh yeah. And then after that, the fifth one is solving the linearized boundary value problem at the actual free surface. The sixth one is apply the solution of the previous step to adjust the free surface elevation according to the linearized dynamic free surface condition. And then the last one, we continue with the step 3 until convergence. This is the zonal approach of the CFD system shift flow, courtesy of Flowtech International AB. So after that, we gain the wave cut analysis, which is the primary aim of the present optimization approach to minimize the total energy losses associated with the wave formation along the hull, which can be measured in terms of the wave pattern resistance. So yeah, as we can see right here, the schematic sketch of the ship wave system only performed in the symmetric half that is considered. Then we do sensitivity analysis, which is the proposed hydrodynamic optimization scheme that utilizes gradients or sensitivity terms for the optimizations. This is the image of outward normal shift of a panel segment at the bow to the right here, of the wiggly hole. So Then we get to do the improvement of the wave making characteristics. The developed hydrodynamic optimization scheme that aims at an improvement of the wave making characteristics and a reduction of the wave or pattern resistance by a favorable variation of the shift fault form. So yeah, we choose the position that we want to be, like this schematic sketch of possible occurrences of induced gaps between adjacent panels. So there is the bottom left, the center one, and the center left position. Right, so I will share one of the applications of this optimization using CFD. The optimization results are discussed in view of the ability of the present optimization scheme to efficiently improve the wave making characteristics. So this is the shape lines of the initial and the bulbous bow optimized of Fantaroro. We see right here, the red line is the initial line that is made by the user. But then after the optimization, we have the optimized line right here. From this table as well, we get to see the length of perpendicular or the length of overall, or any coefficients that will then be optimized. And then we have the sectional areas of the initial and the bulbous bow optimized Fantaroro. This is the detailed magnification of the entrance. Yeah, this is the red one is the initial line. The dark blue one is the optimized, and between them there is a deviation line. Same with this one on the right side, the sectional areas of the initial and the entirely optimized Pantaroro related to the midship sectional area AM of the initial hole. Note that the four perpendicular FP is located at X per LPP equals to 0. Yep, so this is the initial or the top, the bulbous bow optimized or the middle, and the entirely optimized Pantaroro, which is the bottom one. This is the bird's view, this is the fish's view, and the last one is side view. Yeah, we also will gain the wave contours that is enhanced, that is also an enhanced resolution. This is in close proximity to the initial, the top one, to the bulbous bow optimized, the middle one, and to the entirely optimized Pantaroro on the bottom. So yeah, we get to see right here is the wavelength, and the center one is the half of the wavelength itself. Yeah, this is also the bird's view of the wave pattern of the initial port side and the entirely optimized Pantaroro, the starboard side. And the dynamic hole pressure of the initial or the top, the bulbous bow optimized, the middle, and the entirely optimized Pantaroro or the bottom one. So the mathematical model is presented down below, which is the Bernoulli equation that will be used in its linearized version, which should be consistent with the condition of a linearized Dawson free surface boundary. The equation will help calculate the whole surface pressure from the perturbation potential. So we get this equation or this mathematical model as P for pressure plus rho G Z and then plus half of rho point delta point theta, etc. And then now we get the pressure coefficient of or the CP. This is similarly the wave this is similarly the wave profile from equation. And then after that, we will gain the graph of resistance first speed. If the pressure remains constant inside the surface of the hole, the resistance of the wave can be measured. So where delta S is the panel surface area and Nxi denotes the X component. So the result that we get from this optimization is the downflow at the back of the bolt contracts the upflow at the bow stagnation, reducing the bow wave. Furthermore, the narrow waterline entrance angles reduce the bow and the entrance wave. The bulbous bow wave crest and the four shoulder wave through are positioned slightly less than one fundamental wavelength apart from each other. Then the last pronounced wave throw at the evolving aft shoulder is slightly less than half the fundamental wavelength from the four shoulder wave throw. And then the four shoulder wave through and the wave crest aft of the transom in the stern flow are positioned on one fundamental wavelength from each other, which again results in a mutual cancellation. And then the last one, the nearly horizontal flow separation at the transform edge substantially reduces the stern wave and hence the transfer waves which directly follow the ship. So the conclusion that we gain is with the present work, a novel hull form optimization approach has been introduced, which substantially differs from other approaches which address the same objective, like the optimization of the wave making characteristics and the wave or pattern resistance of ships. The optimization process is fully automated, requiring no user interaction, however, permitting it. All aspects of the proposed optimization approach were presented. The application examples clearly show the merits of the method. Naturally, further research is needed to refine the approach to make use of the whole full potential and study its ultimate limitations. So the last one is the references. These are the references that I used to make this final project. So that's all for me. Thank you very much. And I really think that your like on the video will mean the world to me. So once again, thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.